I've been thinking a lot about quantum mechanics, and it's one of those things that when you first encounter it, seems like it should make sense, like it's just another piece of physics, another set of rules about how the world works. But the more you dig into it, the more you realize that actually it's not just another set of rules at all. It's something far stranger, far more unsettling, far more wonderful than anything we could have imagined. Because quantum mechanics doesn't just describe a weird corner of reality that we don't normally encounter. It describes everything. It's the foundation, the bedrock, the actual fabric of existence. And that fabric, well, it doesn't behave anything like we think it should. You see, we live our lives in what physicists call the classical world. Objects have definite positions. They move along predictable paths. If you throw a ball, you can calculate exactly where it's going to land, assuming you know the initial conditions. Cause and effect work the way we expect them to. Things are either here or there, never somehow both, and this makes sense to us, right? It's intuitive. It matches our everyday experience. We've evolved over millions of years to navigate a world where these rules hold, where our intuitions about motion and position and causality are, generally speaking, pretty reliable. But then we look closer. We peer into the realm of atoms and electrons and photons, and suddenly all those intuitions, all those comfortable assumptions about how reality works, they just collapse. They don't apply anymore. Or rather, they're revealed to be approximations, useful fictions that work fine at our scale, but completely fall apart when you get down to the fundamental level. And that's what makes quantum mechanics so profoundly disturbing and so absolutely fascinating. Because it's not that we've discovered some exotic new phenomenon that exists alongside the normal world. We've discovered that the normal world, the classical world we think we know, is actually the exotic special case. The quantum world is the real one. Everything we see, everything we touch, everything we are, it's all built from quantum stuff, from particles that can be in multiple places at once, from systems that remain indefinite until they're measured, from correlations that seem to transcend space and time. We're made of quantum weirdness. Every atom, every molecule, every cell. It's just that somehow when you pile enough of this weirdness together, when you scale up from atoms to objects we can see and touch, the strangeness averages out, and you get something that looks and behaves classically. But underneath, always underneath, it's quantum all the way down. So what is this strangeness? What makes quantum mechanics so different from everything we thought we knew? Well, let's start with one of the most basic, most profoundly weird aspects of the quantum world, something that seems so contradictory, so impossible that even the scientists who discovered it couldn't quite believe it at first. I'm talking about wave-particle duality. And I know you've probably heard this term before, maybe in school or in some documentary. But I want you to really think about what it means, because it's not just a quirky little footnote in physics textbooks. It's a fundamental challenge to how we understand the nature of reality itself. Here's the thing. In the classical world, in our everyday experience, there are waves and there are particles, and they're completely different kinds of things. A wave is something that spreads out, that ripples through a medium, that has properties like wavelength and frequency. Think about ocean waves, or sound waves, or the ripples that spread across a pond when you drop a stone into it. Waves can interfere with each other, creating patterns of reinforcement and cancellation. They can diffract around obstacles. They're extended in space, right? They're not localized to a single point. Particles, on the other hand, they're completely different. A particle is a discrete, localized thing. It has a definite position at any given moment. It follows a specific trajectory. When you throw a rock, it travels along a path, and at each instant, it's at a particular place. Particles can collide with each other like billiard balls. They can be counted. They're fundamentally different from waves in every way we can imagine, except that at the quantum level, this distinction completely breaks down. Light, for instance. For centuries, scientists debated whether light was made of waves or particles. Newton thought it was particles, little corpuscles streaming through space. Then other scientists, like Huygens and later Young and Maxwell, showed that light definitely behaves like a wave. Young's double-slit experiment in 1801 seemed to settle the matter. When you shine light through two narrow slits, you don't get two bright bands on a screen behind the slits, which is what you'd expect if light were made of particles, each particle going through one slit or the other. Instead, you get an interference pattern, alternating bright and dark bands, exactly what you'd expect from waves. When waves from the two slits overlap, they interfere. Where the peaks of the waves align, you get constructive interference, a bright band. Where a peak meets a trough, you get destructive interference, darkness. This is wave behavior, unmistakably, undeniably wave behavior. And then Einstein came along in 1905, the same year he published his theory of special relativity, and he showed that light also behaves like particles. He was trying to explain something called the photoelectric effect, where light shining on a metal surface can knock electrons out of the metal. The weird thing was that the energy of the ejected electrons didn't depend on the intensity of the light, which is what you'd expect if light were a wave. Instead, it depended on the frequency of the light. Shine bright red light on the metal, nothing happens. Shine dim violet light, and electrons come flying out. Einstein explained this by proposing that light comes in discrete packets, quanta, which we now call photons. Each photon has an energy proportional to its frequency. An electron absorbs a single photon, and if that photon has enough energy, the electron escapes the metal. More intense light just means more photons, but if each individual photon doesn't have enough energy, no electrons get ejected. This is particle behavior. Light, somehow, is both a wave and a particle. But it gets stranger, because it's not just light, it's everything. In the 1920s, Louis de Broglie proposed that if light, which we thought was a wave, can behave like a particle, then maybe particles, things like electrons, could behave like waves, and he was right. In 1927, Clinton Davison and Lester Germer shot electrons at a crystal and observed a diffraction pattern exactly like the diffraction pattern you get when you shine light through a grating. Electrons, these tiny bits of matter that we think of as the ultimate particles, were behaving like waves. They were spreading out, interfering with themselves, creating patterns that only waves can create. And this is where it gets really, really strange. Because when you actually do the double slit experiment with electrons, sending them one at a time through the apparatus, something deeply unsettling happens. You'd think, okay, each electron is a particle, it's going to go through one slit or the other, and eventually you'll build up two bands on the detector screen, one behind each slit, but that's not what happens. Instead, even when you send the electrons through one at a time, even when there's only ever one electron in the apparatus at any given moment, you still get an interference pattern. Each electron somehow interferes with itself. It's as if the electron goes through both slits simultaneously, like a wave, and then interferes with itself on the other side. But when it hits the detector screen, it arrives as a particle, as a single localized dot. Over time, as you build up thousands or millions of these dots, the pattern that emerges is an interference pattern, the signature of wave behavior. So each individual electron is somehow both a wave and a particle. It travels like a wave, spreading out, exploring multiple paths, interfering with itself. But it's detected like a particle, arriving at a single point. Now you might think, well, maybe the electron really does go through one slit, and something about our apparatus is creating the interference pattern. So scientists tried something. They set up detectors at the slits to see which slit each electron actually goes through. And here's where quantum mechanics reveals its truly bizarre nature. When you watch which slit the electron goes through, when you measure its path, the interference pattern disappears. Instead, you get exactly what you'd expect from classical particles. Two bands, one behind each slit. The act of measuring, of determining which path the electron took, fundamentally changes the behavior of the electron. When you're not looking, it behaves like a wave going through both slits. When you are looking, it behaves like a particle going through one slit or the other. The electron somehow knows whether it's being watched, or rather, it exists in a fundamentally different state depending on whether a measurement is being made. This is what physicists call the measurement problem, and it's one of the deepest, most philosophically troubling aspects of quantum mechanics. Because it seems to suggest that the act of observation, the act of measurement, plays a fundamental role in determining what's real. Before you measure, the electron isn't simply at a definite position that you don't know about. It's genuinely in a superposition of multiple states simultaneously. It really is going through both slits at once in some sense. And when you measure it, when you interact with it in a way that forces it to reveal a definite property, the superposition collapses and the electron suddenly has a definite position, a definite path. But until that measurement happens, it's in this strange, indefinite state that has no analog in our classical experience. And this isn't just about electrons or photons. This is a fundamental feature of quantum mechanics. Every quantum system exists in a superposition of multiple possible states until a measurement is made. It's described by something called a wave function, which is a mathematical object that encodes all the possible states the system could be in, along with the probability of finding it in each state if you were to measure it. The wave function evolves smoothly and deterministically according to the Schrödinger equation, spreading out, exploring all possible paths, interfering with itself. But when you make a measurement, something different happens. The wave function collapses, suddenly and randomly, to one of the possible outcomes. And we don't really understand why this happens. We don't know what counts as a measurement. We don't know what triggers the collapse. It's one of the great mysteries of quantum mechanics, and different interpretations of quantum theory give different answers, none of them entirely satisfying. But let's step back for a moment, because I want to talk about what this superposition actually means, what it implies about the nature of reality. The most famous illustration of this is Schrödinger's cat, a thought experiment that Schrödinger himself proposed, not to celebrate quantum mechanics, but actually to critique it, to show how absurd the theory seemed when you applied it to everyday objects. Here's how it goes. You put a cat in a sealed box, along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter detects it and triggers a mechanism that breaks the vial, releasing the poison and killing the cat. Radioactive decay is a quantum process, genuinely random, with a 50-50 chance of occurring within a certain time period. So, according to quantum mechanics, until you open the box and observe the system, the atom is in a superposition of decayed and not decayed. And if the atom is in a superposition, then the Geiger counter is in a superposition of triggered and not triggered. And if the Geiger counter is in a superposition, then the cat is in a superposition of alive and dead. Now that sounds insane, right? A cat that's somehow both alive and dead at the same time? Schrödinger's point was exactly that. This seems absurd, and therefore there must be something wrong with quantum mechanics, or at least with how we're interpreting it. But here's the thing. Every test we've ever done, every experiment we've ever performed, confirms that quantum mechanics is correct. The predictions it makes are borne out with astonishing precision, so we're left with this deeply uncomfortable conclusion. At some level, superposition is real. The cat really is in an indefinite state until you open the box. Or at least the atom and the Geiger counter and all the quantum systems involved really are in superposition, and somehow, when these quantum systems interact with something big and classical like you, the observer, the superposition collapses and the cat ends up definitely alive or definitely dead. But why? What makes you, the observer, special? What counts as a measurement? Is it consciousness? Does the cat count as an observer? Does the Geiger counter? These are questions that have plagued physicists and philosophers for nearly a century, and we still don't have agreed upon answers. Some interpretations of quantum mechanics, like the Copenhagen interpretation that Bohr and Heisenberg developed, basically say that measurement is fundamental, that the quantum world and the classical world are just different, and the transition between them happens when a measurement occurs, but we can't say anything more specific than that. Other interpretations, like the many worlds interpretation proposed by Hugh Everett, say that there is no collapse at all. Instead, every time a quantum measurement could have multiple outcomes, the universe splits into multiple branches, one for each outcome. In one branch, the cat is alive. In another, it's dead. Both branches are equally real, and you, the observer, split as well, so there's a version of you that sees a live cat and a version that sees a dead cat. This sounds even more bizarre than the original problem, but it has the advantage of being mathematically clean. There's no mysterious collapse, no special role for measurement, just the smooth, deterministic evolution of the universal wave function, branching endlessly into myriad parallel worlds. And that's the kind of thing that keeps physicists up at night, because we're not just talking about abstract mathematics here, we're talking about the nature of reality. Are there really countless parallel universes constantly splitting off every time a quantum event has multiple possible outcomes? Or is there something special about observation, something we don't yet understand, that causes wave functions to collapse? Or is there some other explanation entirely that we haven't thought of yet? These aren't just philosophical curiosities. They're genuine gaps in our understanding of how the universe works at its most fundamental level. But let's move on to another aspect of quantum strangeness, something that Einstein himself called spooky action at a distance, something that bothered him so much that he spent years trying to prove that quantum mechanics must be incomplete. I'm talking about entanglement, and this is where quantum mechanics goes from being weird and counterintuitive to being downright impossible according to our classical intuitions about how reality should work. Here's the basic idea. When two quantum particles interact, they can become entangled, meaning that their states become correlated in a way that can't be explained by classical physics. Once entangled, the particles remain connected no matter how far apart they are. If you measure a property of one particle, you instantaneously know something about the other particle, even if it's on the other side of the universe. Now, that might not sound too strange at first. You could imagine classical correlations, right? Like suppose I tear a piece of paper in half, put each half in an envelope, and send one to you and keep one for myself. When you open your envelope and see that you have the left half, you instantly know that I have the right half. That's a correlation, but it's not mysterious. The paper was torn into left and right halves from the beginning. You just didn't know which one you had until you looked. But quantum entanglement is different. It's not that the particles have definite properties all along, and we just don't know what they are. Before measurement, the particles genuinely don't have definite values for certain properties. They're in a superposition, but they're in a special kind of superposition where the states of the two particles are linked. The classic example is spin. Quantum particles, like electrons, have a property called spin, which you can think of very roughly as the particle spinning around an axis, though that's not really what it is. When you measure an electron's spin along a particular axis, you get one of two outcomes: spin up or spin down. Before measurement, the electron is in a superposition of both. Now you can create a pair of entangled electrons where their total spin is zero. If one is spin up, the other must be spin down, and vice versa. But before you measure either one, neither electron has a definite spin. They're both in superposition. Now here's where it gets spooky. Suppose you take these two entangled electrons and separate them by a large distance, say one is on Earth and one is on the Moon. You measure the spin of the electron on Earth and you find that it's spin up. Instantly, at that very moment, the electron on the Moon becomes spin down. Not because some signal traveled from Earth to the Moon telling it what to do. Not because the electron on the Moon was spin down all along and you just didn't know it. But because the measurement of one particle instantaneously collapses the entangled wave function of both particles, determining their states simultaneously. Einstein hated this. He, along with Boris Podolsky and Nathan Rosen, wrote a famous paper in 1935, the EPR paper, arguing that this proved quantum mechanics was incomplete. There must be some hidden variables, some deeper layer of reality that we're not seeing that determines the particle's properties in advance. The alternative, that measuring one particle could instantaneously affect another particle arbitrarily far away, seemed to violate the principle that nothing can travel faster than light, a cornerstone of Einstein's own theory of relativity. But then, in the 1960s, a physicist named John Bell came up with a way to test this. He derived what are now called Bell inequalities, mathematical constraints that any theory based on local hidden variables must satisfy. And then experiments were done, most famously by Alain Aspect in the 1980s, and they showed that Bell's inequalities are violated. Nature does not obey the constraints that local hidden variables would impose. The correlations between entangled particles are stronger than any classical explanation can account for. Entanglement is real, and it really does seem to involve some kind of instantaneous connection between particles, regardless of the distance between them. Now, before you get too worried, this doesn't actually allow for faster than light communication. You can't use entanglement to send information from Earth to the Moon instantly, because the outcome of measuring an entangled particle is random. You can't control what result you'll get, so you can't encode a message in the measurement outcomes. The person on the Moon measuring their particle will get a random sequence of ups and downs, and they won't know that these outcomes are correlated with yours until you compare notes later through some classical communication channel, which is limited by the speed of light. but the correlation itself, the connection between the particles, that does seem to be instantaneous. It's as if the two particles, once entangled, remain part of a single quantum system, no matter how far apart they are in space. Space, at the quantum level, doesn't seem to work the way we think it does. Particles that are widely separated in space can still be deeply connected, still be part of the same quantum state, still affect each other in ways that transcend spatial separation. And this has profound implications, not just for physics, but for our understanding of reality. It suggests that the universe is fundamentally non-local, that the old idea of local realism, the idea that objects have definite properties independent of observation, and that interactions between objects are limited by the speed of light, is just wrong. The universe doesn't work that way. At the quantum level, reality is holistic, interconnected, entangled in ways that defy our classical intuitions. And this isn't just theoretical. Entanglement is being used in real technologies. Quantum computing relies on entanglement to perform computations that would be impossible for classical computers. Quantum cryptography uses entanglement to create communication channels that are, in principle, perfectly secure, because any attempt to intercept the communication would disturb the entangled state and be detectable. This is quantum mechanics not as an abstract theory, but as a practical tool, as technology that's beginning to reshape the world. But let's talk about another fundamental aspect of quantum weirdness, something that's encapsulated in what's called the Heisenberg uncertainty principle. Now, you've probably heard of this, and you might have heard it explained as something like, you can't measure both the position and momentum of a particle at the same time because measuring one disturbs the other. And that's sort of true, but it's not the whole story, and it's not really the deepest part of what the uncertainty principle is telling us. The uncertainty principle, at its core, says that there are pairs of properties, like position and momentum, that fundamentally cannot both have definite values at the same time. It's not that the particle has a definite position and a definite momentum, and we just can't measure them both accurately. It's that the particle genuinely doesn't have both a definite position and a definite momentum simultaneously. If you know the position very precisely, then the momentum is very uncertain, not just unknown, but genuinely indefinite. And if you know the momentum precisely, then the position is uncertain. These properties are complementary. The more definite one is, the less definite the other is. And this is built into the mathematical structure of quantum mechanics. It's a consequence of the wave-particle duality, of the fact that quantum objects are described by wave functions that have to obey certain mathematical relationships. Think about it this way. If a particle has a very definite momentum, that means its wave function is a smooth extended wave with a well-defined wavelength. But a smooth extended wave doesn't have a definite position. It's spread out over space. On the other hand, if you want the particle to have a very definite position, you need the wave function to be sharply peaked, localized to a small region. But to make a sharp peak, you have to add together waves with many different wavelengths, which means many different momenta. So a precise position implies an uncertain momentum, and vice versa. It's not a limitation of our measuring devices. It's a fundamental feature of how quantum systems work. And this has strange consequences. One of the most striking is something called quantum tunneling. In classical physics, if a particle doesn't have enough energy to overcome a barrier, it can't get through. Imagine rolling a ball toward a hill. If the ball doesn't have enough speed to reach the top of the hill, it'll roll back down. It can't spontaneously appear on the other side of the hill. But in quantum mechanics, because particles don't have definite positions, because they're described by wave functions that spread out and penetrate into regions where classical particles couldn't go, there's a non-zero probability that a particle can tunnel through a barrier even if it doesn't have enough energy to go over it. The wave function extends into and through the barrier, and there's a chance that the particle will be found on the other side. This sounds like pure science fiction, but it's not. It happens all the time. It's the reason that certain kinds of radioactive decay occur. Atomic nuclei are held together by the strong nuclear force, which creates a potential barrier. An alpha particle inside a nucleus doesn't have enough energy to escape classically. But quantum mechanically, it can tunnel through the barrier, and occasionally it does. That's alpha decay. And it's not just radioactivity. Quantum tunneling is essential to the operation of many modern electronic devices. Tunnel diodes, flash memory, scanning, tunneling microscopes, they all rely on quantum tunneling. And on a more cosmic scale, quantum tunneling is what allows nuclear fusion to occur in the cores of stars. The protons in a star's core are positively charged, so they repel each other electromagnetically. At the temperatures in a star, protons don't have enough energy to overcome this repulsion classically. But quantum tunneling allows them to get close enough for the strong nuclear force to bind them together, creating fusion reactions that power the star. Without quantum tunneling, stars wouldn't shine, the sun wouldn't exist, we wouldn't exist. So quantum mechanics isn't just some abstract theory about things happening in laboratories. It's the foundation of reality. It determines how atoms bond to form molecules, how electrons move in materials, how light interacts with matter, how stars burn, how the universe evolves. Everything around you, everything you see and touch is governed by quantum mechanics. It's just that in most everyday situations, the quantum effects are too small to notice, or they average out over large numbers of particles, giving rise to the classical behavior we're familiar with. But the quantum world is always there, underneath, the true foundation of existence. Now, I want to take a step back and talk about how we got here, how this strange, counterintuitive theory came to be, because the history of quantum mechanics is almost as fascinating as the theory itself. It's a story of brilliant minds grappling with observations that didn't make sense, of intense debates about the nature of reality, of radical new ideas that challenged everything physicists thought they knew. It really started in 1900 with a problem about blackbody radiation. A blackbody is an idealized object that absorbs all the light that hits it and emits light based only on its temperature. Physicists had a formula based on classical physics for predicting the spectrum of light emitted by a blackbody, but it didn't match the experimental data. At high frequencies, the formula predicted infinite energy, something called the ultraviolet catastrophe, which was obviously wrong. Max Planck, trying to fix this problem, made a radical assumption. He proposed that energy could only be emitted or absorbed in discrete chunks, quanta, with the energy of each quantum proportional to the frequency of the light. This wasn't based on any deep physical principle. It was more of a mathematical trick that happened to give the right answer, but it worked, and it introduced the idea that energy comes in discrete units, that there's a fundamental graininess to nature. Then Einstein came along and took this seriously. He used Planck's idea to explain the photoelectric effect, proposing that light really does come in discrete particles, photons. And this was revolutionary because everyone thought light was a wave. Maxwell's equations described light as an electromagnetic wave, and that theory had been spectacularly successful. But Einstein was saying, no, light is also made of particles. And he was right. Then, in the 1910s and 1920s, Niels Bohr developed his model of the atom, where electrons orbit the nucleus in specific quantized orbits. Electrons could only be in certain orbits with certain energies, and when they jumped from one orbit to another, they emitted or absorbed a photon with an energy equal to the difference between the orbit energies. This explained the spectral lines of hydrogen, the specific frequencies of light that hydrogen atoms emit or absorb. But Bohr's model was kind of ad hoc. It worked, but it wasn't based on a deeper principle. It was just a set of rules that happened to match the data. The real breakthrough came in the mid-1920s when several physicists working independently, and sometimes in competition, developed the full theory of quantum mechanics. Heisenberg came up with matrix mechanics, a formulation based on matrices and operators. Schrödinger developed wave mechanics based on his famous wave equation. And then it was shown that these two approaches were actually mathematically equivalent, just different ways of describing the same underlying theory. Dirac further developed the mathematical framework, and Born provided the probabilistic interpretation of the wave function. By the late 1920s, quantum mechanics was essentially complete, at least in its basic formulation. And it worked. It made predictions that were confirmed by experiment after experiment. It explained atomic structure, chemical bonding, the behavior of materials, the emission and absorption of light. It was and remains one of the most successful theories in the history of science. But from the very beginning, physicists were uncomfortable with it because it challenged fundamental assumptions about how science works. about what we can know, about what is real. Einstein famously never accepted the probabilistic nature of quantum mechanics. His famous quote, "God does not play dice with the universe," reflected his belief that quantum mechanics, with its inherent randomness, couldn't be the final story. There must be some deeper deterministic theory underneath. But every attempt to find such a theory to restore determinism to quantum physics has failed. The randomness seems to be fundamental, not just a reflection of our ignorance. Bohr and Einstein had a series of debates, sometimes friendly, sometimes heated, about the interpretation of quantum mechanics. Bohr defended what became known as the Copenhagen interpretation, which basically says that quantum mechanics is complete, that the wave function is all there is, that observation plays a fundamental role in determining reality, and that we have to accept that certain questions like where is the electron before we measure it simply don't have answers. Einstein kept trying to come up with thought experiments that would show contradictions or incompleteness in quantum mechanics. The EPR paper was one such attempt, but each time Bohr would respond with arguments showing that quantum mechanics was consistent, that there was no contradiction, just a reality that didn't conform to classical expectations. And this debate, this tension between those who were willing to accept the strangeness of quantum mechanics and those who felt there must be something more, something deeper, has continued to this day, because quantum mechanics works. It makes predictions, and those predictions are confirmed with astonishing accuracy. The anomalous magnetic moment of the electron, for instance, has been calculated using quantum electrodynamics, the quantum theory of how light and matter interact. And the theoretical prediction agrees with experimental measurement to about 10 decimal places. That's an extraordinary level of precision. No other theory in physics comes close. But despite this success, we still don't fully understand what quantum mechanics is telling us about the nature of reality. There are many interpretations of quantum mechanics, different ways of understanding what the math means, what the wave function represents, what happens during measurement. The Copenhagen interpretation, as I mentioned, says that measurement is fundamental and that certain questions don't have answers. The many worlds interpretation says that all possible outcomes of a quantum measurement actually occur in different branches of the universe. The pilot wave theory, or de Broglie-Bohm theory, says that particles do have definite positions all the time, but they're guided by a wave that follows the Schrödinger equation. This restores determinism, but requires non-local connections between particles. Then there are newer ideas like quantum Bayesianism or cubism, which interprets quantum mechanics as a set of rules for updating an observer's beliefs, rather than as a description of objective reality. And there are others, each with its own strengths and weaknesses, each offering a different perspective on what quantum mechanics means. The thing is, these interpretations all make the same experimental predictions, at least as far as we've been able to test. They differ in what they say about the underlying reality, about what's really going on, but they agree on what we'll observe in any given experiment. So how do we choose between them? That's more a matter of philosophy than physics. It depends on what you think a scientific theory should do, what kinds of explanations you find satisfying, what assumptions about reality you're willing to make. Some physicists even say that these questions don't matter, that as long as quantum mechanics makes correct predictions, it doesn't matter what interpretation you prefer. But I think that's unsatisfying because we're not just trying to predict experimental outcomes. We're trying to understand the world. We want to know what's real, how reality works, not just what numbers will appear on our detectors. And this brings us to some of the deeper philosophical questions that quantum mechanics raises. Questions about the nature of reality, about causality, about determinism and free will, about the role of observers and consciousness. Because if the act of observation plays a fundamental role in determining what's real, as the Copenhagen interpretation suggests, then what does that mean? Does consciousness create reality? That seems absurd, but some people have taken it seriously. The physicist John Wheeler proposed something he called the participatory universe, the idea that observers are not just passive viewers but active participants in creating reality. And there's a related idea, the anthropic principle, which says that the universe must be such that it allows for observers to exist, because if it weren't, we wouldn't be here to observe it. In its strong form, this gets into territory that sounds almost mystical, suggesting that the universe exists for the purpose of being observed. Most physicists are uncomfortable with these ideas. They seem to grant too much importance to observers, to consciousness, which seems unscientific. But the measurement problem remains. We don't know what causes wave function collapse, what distinguishes a measurement from any other physical interaction. Some physicists think the answer will come from understanding how quantum systems interact with large, complex environments, a process called decoherence. When a quantum system becomes entangled with its environment, the coherent superpositions that give rise to quantum behavior are very quickly destroyed, and the system starts to behave classically. This might explain why we don't see quantum superpositions in everyday life. But decoherence doesn't really solve the measurement problem, because it doesn't explain why a particular outcome is obtained in any given measurement. It just explains why we don't see superpositions of macroscopic objects. The wave function of the system plus environment is still in superposition. We've just spread the problem out over a larger system, so the measurement problem remains one of the great unsolved mysteries of quantum mechanics, and tied to it are questions about causality and determinism. In classical physics, if you know the exact state of a system at one time and you know the laws of physics, you can predict in principle the exact state of the system at any future time. The universe is deterministic, a giant clockwork mechanism. But quantum mechanics is different. Even if you know the wave function exactly, even if you have complete information about a quantum system, you can't predict with certainty what will happen when you measure it. You can only predict probabilities. The outcome of a measurement is genuinely random, not just unpredictable because of our ignorance, but fundamentally indeterminate. And this has led some people to argue that quantum mechanics restores free will, that the randomness of quantum events means that the future is not determined by the past, that there's room for genuine choice and agency. Others think this is a non sequitur, that random quantum events have nothing to do with free will, which is about intentional, purposeful action, not randomness. These are deep questions, and quantum mechanics forces us to confront them in ways that classical physics never did. Because classical physics was so intuitively sensible, so aligned with our everyday experience, it was easy to think we understood it, that we knew what it meant. But quantum mechanics doesn't allow that comfort. It presents us with a picture of reality that is strange, counterintuitive, and profoundly mysterious, and yet it works. It describes the world accurately. So we're forced to grapple with the possibility that reality really is this strange, that our intuitions, shaped by evolution to navigate the macroscopic world, are simply inadequate for understanding the fundamental nature of existence. Now, I want to talk about some of the modern developments in quantum mechanics, the ways that our understanding has deepened and the new technologies that are emerging from this strange science, because quantum mechanics isn't just an abstract theory. It's becoming a practical tool, a foundation for new kinds of technology that were unimaginable a few decades ago. One of the most exciting developments is quantum computing. Classical computers process information in bits, which can be either 0 or 1. A quantum computer uses quantum bits or qubits, which can be in a superposition of 0 and 1 simultaneously. This means that a quantum computer can, in a sense, explore many possible solutions to a problem at the same time. For certain kinds of problems, this gives quantum computers an exponential advantage over classical computers. Factoring large numbers, for instance, is extremely difficult for classical computers. The difficulty of factoring is the basis for many encryption schemes used to secure internet communications. But Peter Shor showed in 1994 that a quantum computer could factor large numbers exponentially faster than any known classical algorithm. This means that if large-scale quantum computers are built, they could break most of the encryption currently used to protect sensitive data. That's both exciting and terrifying. But quantum computers could do much more than break codes. They could simulate quantum systems directly, which would allow us to design new materials, new drugs, new chemical processes by simulating how molecules interact at the quantum level. Classical computers struggle with this because the complexity of quantum systems grows exponentially with the number of particles. But a quantum computer, being itself a quantum system, could handle this naturally. And there are other problems in optimization, machine learning, and other areas where quantum computers could provide significant advantages. The challenge is building them. Qubits are extremely fragile. They're quantum systems, which means they're susceptible to decoherence. Any interaction with the environment can cause the qubits to lose their quantum properties, to collapse out of superposition, which destroys the computation. So quantum computers have to be extremely well isolated from their environment, typically operating at temperatures close to absolute zero, and even then, errors accumulate. Building a quantum computer that can perform useful computations requires not just creating qubits, but developing error correction techniques that can protect the quantum information from noise and decoherence. This is a huge engineering challenge, and it's not clear yet whether large-scale, fault-tolerant quantum computers are practically achievable. But enormous progress has been made in recent years. Companies like IBM, Google, and others have built small quantum computers with dozens of qubits, and they're working on scaling up. Google even claimed in 2019 to have achieved quantum supremacy, demonstrating a quantum computer performing a calculation that would be infeasible for the most powerful classical supercomputers. The claim is contested, and the calculation itself was somewhat artificial, chosen specifically to favor quantum computers, but it was still a milestone. Another area where quantum mechanics is having an impact is quantum cryptography, which I mentioned earlier. The most developed application is quantum key distribution, or QKD. The basic idea is that you can use entangled particles to establish a shared secret key between two parties in such a way that any attempt to intercept the key would disturb the quantum state and be detectable. This provides, in principle, perfect security guaranteed by the laws of physics rather than by the difficulty of mathematical problems. QKD systems have been built and are even commercially available, though they're still limited by distance and require direct fiber optic connections or line-of-sight links. Researchers are working on quantum repeaters, devices that could extend the range of quantum communication by entangling particles across multiple segments, potentially enabling a global quantum internet. There's also growing interest in quantum sensors, devices that exploit quantum effects to make extremely precise measurements. Quantum entanglement and superposition can be used to measure time, magnetic fields, gravitational fields, and other quantities with unprecedented accuracy. Atomic clocks, which are the most accurate timekeeping devices we have, are based on quantum transitions in atoms. Newer designs using entangled atoms could improve their accuracy even further. Quantum magnetometers could detect incredibly weak magnetic fields, useful for medical imaging, mineral exploration, and fundamental physics research. And quantum gravimeters could measure tiny variations in gravity, useful for studying Earth's subsurface, detecting underground structures, or even testing fundamental theories of gravity. So quantum mechanics, this strange counterintuitive theory that emerged from trying to understand the behavior of atoms and light, is becoming a technological foundation. The weird features that puzzled and disturbed the founders of quantum mechanics, superposition, entanglement, uncertainty, are now being harnessed as resources for computation, communication, and sensing. The quantum world, once seen as a mysterious, inaccessible realm, is becoming something we can engineer and control. But even as we develop these technologies, there are still fundamental aspects of quantum mechanics that we don't fully understand. One of the biggest open questions is how to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. These are our two most fundamental theories of physics. Quantum mechanics describes the behavior of matter and energy at small scales, the interactions of particles and fields. General relativity describes gravity, the curvature of space-time, the large-scale structure of the universe, and both theories are extraordinarily successful in their respective domains, but they seem to be incompatible with each other. General relativity is a classical theory. It describes space-time as a smooth, continuous manifold. Quantum mechanics is, quantum based on discrete states and probabilities. When you try to apply quantum mechanics to gravity, when you try to quantize general relativity, you run into problems. The math doesn't work. You get infinities that can't be removed, predictions that are nonsensical. Physicists have been trying for decades to develop a theory of quantum gravity, a unified framework that incorporates both quantum mechanics and general relativity. There are several candidates. String theory proposes that fundamental particles are not point-like, but are actually tiny, vibrating strings. In this framework, gravity emerges naturally as one of the vibrational modes of the string. String theory requires extra spatial dimensions beyond the three we observe, typically 6 or 7 extra dimensions that are curled up so small we can't detect them. It's mathematically elegant, and it naturally includes gravity, but it's extraordinarily difficult to test. The energy scales where string effects become important are far beyond what we can access in particle accelerators. And string theory hasn't yet made any definite testable predictions that distinguish it from other theories. Another approach is loop quantum gravity, which tries to quantize space-time itself. In this theory, space is not continuous, but is made of discrete quantum units, tiny loops of space-time at the Planck scale, about 10 to the negative 35th meters. Space-time is woven from these loops, and what we perceive as smooth space is an approximation that emerges when you average over many loops. Loop quantum gravity doesn't require extra dimensions, and it's more directly connected to general relativity, but it also faces challenges in making testable predictions and in showing how classical space-time emerges from the quantum structure. There are other ideas too. Causal set theory, which represents space-time as a discrete set of events with causal relations between them. Asymptotically safe gravity, which tries to find a way to quantize gravity that avoids infinities. Approaches based on information theory that suggests space-time and gravity might be emergent from more fundamental quantum information, but none of these has been definitively confirmed or ruled out. We're still searching for the right framework, the right way to think about quantum gravity. And this is not just an academic question. Quantum gravity is essential for understanding the earliest moments of the Big Bang, the insides of black holes, the ultimate fate of the universe. These are situations where both quantum effects and gravitational effects are important, and we can't fully describe them without a theory that unifies both. Another frontier is understanding the quantum properties of space-time itself. In quantum mechanics, everything fluctuates. The uncertainty principle means that energy, position, momentum, even time have inherent uncertainties. And if space-time is quantum, then space-time itself should fluctuate. At very small scales, close to the Planck length, space-time might be a roiling foam of quantum fluctuations, with virtual particles and black holes constantly popping into and out of existence. This is far beyond anything we can directly observe, but it might have subtle effects that we could detect. Some theories predict that quantum gravity effects might cause tiny violations of Lorentz invariance, the principle that the laws of physics are the same in all inertial frames, or they might affect the propagation of light from distant sources like gamma-ray bursts. Astronomers are looking for such effects, but so far, nothing definitive has been found. There's also the mystery of dark matter and dark energy. Observations tell us that the visible matter in the universe, stars, planets, gas, everything made of atoms and light, accounts for only about 5% of the total mass energy of the universe. About 27% is dark matter, which doesn't emit or absorb light, but exerts gravitational influence, holding galaxies together and affecting the structure of the cosmos. And about 68% is dark energy, a mysterious form of energy that permeates space and is causing the expansion of the universe to accelerate. We don't know what dark matter or dark energy are. They're not explained by the standard model of particle physics, our best quantum theory of matter. Dark matter might be some new type of particle that interacts very weakly with ordinary matter, perhaps detectable only through gravity and rare collisions with atomic nuclei. Huge detectors deep underground are searching for such collisions, but so far dark matter has remained elusive. Dark energy is even more mysterious. It behaves almost like a cosmological constant, a constant energy density filling all of space, but we don't know why it has the value it does. In fact, when physicists try to calculate the vacuum energy density from quantum field theory, they get a result that's about 120 orders of magnitude larger than the observed dark energy. This is called the cosmological constant problem, and it's one of the worst discrepancies between theory and observation in all of physics. Something is deeply wrong with our understanding here, and resolving it might require new insights into quantum mechanics, gravity, or both. And then there's the question of the quantum nature of time itself. In quantum mechanics, time is treated differently from space. Space is quantized in the sense that position is an operator, a quantum observable, But time is just a parameter, a label for when things happen. In general relativity, time and space are unified into space-time, and time can be warped and curved just like space. So how do we reconcile these pictures? Is time fundamentally quantum? Does it make sense to talk about a superposition of different times the way we talk about superposition of different positions? Some approaches to quantum gravity suggest that time might emerge from something more fundamental, that at the deepest level there is no time, only timeless quantum states, and what we perceive as time is an emergent property that arises when we consider large, complex systems. This is a radical idea, and it's far from proven, but it's taken seriously by some physicists working on the foundations of quantum gravity. And speaking of time, there's also the question of the arrow of time, why time seems to flow in one direction from past to future. The fundamental laws of physics, both classical and quantum, are time reversible. They work the same whether you run time forward or backward. But we experience a clear direction to time. We remember the past, not the future. We age. Eggs break but don't spontaneously reassemble. Entropy, the measure of disorder, increases over time. This is the second law of thermodynamics, and it gives time its arrow. But why? The second law is statistical. It's not that entropy can't decrease, but that it's overwhelmingly unlikely for a large system. But this seems to push the question back. Why did the universe start in a low entropy state, allowing entropy to increase over time? And does this have anything to do with quantum mechanics, with the measurement problem, with the collapse of the wave function, which also seems to be an irreversible process? These are deep questions, and we don't have answers, but they're being actively researched. Physicists and philosophers are thinking hard about the foundations of quantum mechanics, about what it tells us about time, causality, and reality. And experiments are becoming increasingly sophisticated, probing quantum phenomena in new regimes, testing the boundaries of quantum behavior, looking for deviations from standard quantum mechanics that might point the way to a deeper theory. For instance, there are experiments testing quantum mechanics in ever larger systems. We've seen interference and superposition in particles, in atoms, in small molecules. But can you create superposition in larger objects? In recent years, physicists have demonstrated quantum effects in objects with billions of atoms, in tiny mechanical resonators, in superconducting circuits large enough to be visible to the naked eye. Each step up in size is a challenge, because larger objects interact more strongly with their environment, causing decoherence. But by carefully isolating systems and using clever techniques, researchers are pushing into new territory. If quantum mechanics applies to all systems, no matter how large, then in principle, you could create a superposition of a cat or a person or even larger objects. But in practice, decoherence happens so quickly for large objects that such superpositions exist only for unimaginably brief moments. Still, exploring this boundary, understanding where and why quantum behavior gives way to classical behavior, could teach us something fundamental about how quantum mechanics works. There are also tests of quantum mechanics over long distances. Entanglement has been demonstrated between particles separated by hundreds of kilometers using satellites to distribute entangled photons across the globe. These tests confirm that quantum mechanics works the same way even at these large scales, and they also test whether there might be some subtle effect, some modification to quantum mechanics that becomes apparent over long distances. So far, nothing has been found. Quantum mechanics remains consistent, and there are tests looking for tiny effects that might hint at new physics. For example, some theories of quantum gravity predict that space-time is not perfectly continuous, but has a discrete structure at the Planck scale. This might cause very high-energy photons to travel at slightly different speeds than lower-energy photons, an effect that could accumulate over vast distances. By observing gamma-ray bursts from the distant universe, astronomers can look for such effects. Again, so far, nothing definitive has been found, but the searches continue. All of this is to say that quantum mechanics, despite being nearly a century old, is still a vibrant, active field of research. We're not just applying it and developing technologies, we're still trying to understand what it means, what it tells us about reality. And there's a sense, among many physicists, that we haven't yet reached the end. That quantum mechanics, as successful as it is probably not the final theory. It might be part of a larger framework, something that unifies quantum mechanics and gravity, something that explains the measurement problem, something that tells us what dark matter and dark energy are, something that gives us a deeper understanding of space, time, and causality. We don't know what this larger framework is, or if it even exists. But the fact that there are still deep mysteries, still unanswered questions, still places where our theories break down or leave us puzzled, that's exciting. That means there's more to discover, and I think that's one of the beautiful things about science, about physics in particular. We're trying to understand the universe at its most fundamental level. We're asking the biggest, deepest questions. What is reality? How does it work? Why is there something rather than nothing? And we're making progress. Slowly, painstakingly, through careful observation, clever experiments, and brilliant theoretical work, we're uncovering the secrets of nature. Quantum mechanics is a huge part of that story. It's taught us that reality is far stranger than we imagined, that the universe doesn't obey our intuitions, that there are limits to what we can know. But it's also taught us that we can understand this strangeness, that we can develop theories that describe it, make predictions, and build technologies based on it. We live in a quantum universe, and we're learning to navigate it, to harness it, to make it part of our understanding of existence. So when you think about quantum mechanics, don't just think about it as an abstract theory, as a set of equations in a textbook. Think about it as a window into the deepest nature of reality. Think about the fact that you right now are made of atoms, and those atoms are quantum systems, existing in superpositions, entangled with the world around you, obeying the strange rules of the quantum world. Every chemical bond in your body, every electrical signal in your brain, every photon of light entering your eyes, it's all quantum mechanics, all the way down. And think about the fact that we've figured this out, that we've peered into the quantum realm and uncovered its secrets, despite how alien and counterintuitive it is. That's an extraordinary achievement, a testament to human curiosity, creativity, and persistence. But also think about what we don't know. Think about the measurement problem, about why wave functions collapse, about what happens in a quantum measurement. Think about entanglement, about how particles separated by vast distances remain connected in ways that seem to transcend space. Think about the uncertainty principle, about the fundamental limits on what can be known, about how the universe seems to resist our attempts to pin everything down. Think about superposition, about how systems can exist in multiple states at once, in a way that defies classical logic. Think about how all of this might connect to gravity, to space-time, to the large-scale structure and evolution of the cosmos. Think about the open questions, the mysteries that remain, the places where our understanding runs out. Because that's where the frontier is, that's where the next generation of physicists will work, where new discoveries will be made, where our understanding of the universe will deepen and evolve. Quantum mechanics has taken us a long way, but the journey isn't over. There's more to learn, more to discover, more to understand, and that's what makes this so exciting. We're not at the end of physics. We're not even close. We're still in the early stages of understanding the universe, still uncovering layer after layer of complexity and beauty. Quantum mechanics is one of those layers, a deep, fundamental one, but there are almost certainly more layers beneath it, more secrets waiting to be revealed. And maybe that's the most important thing quantum mechanics teaches us, not just the specific facts about superposition and entanglement and uncertainty, but the broader lesson that reality is not what we expect, that the universe is under no obligation to make sense to us, to conform to our intuitions. We evolved to survive in a world of medium-sized objects moving at medium speeds, and our brains are wired to understand that world. But the universe is far larger, far older, far stranger than the slice of it we directly experience. And if we want to understand it, we have to be willing to let go of our preconceptions, to accept that our intuitions might be wrong, to follow the evidence wherever it leads, no matter how bizarre the destination. Quantum mechanics forces us to do that. It presents us with a reality that seems impossible, that violates our deepest assumptions about how things should work. And yet, it's true. Every experiment confirms it. Every technology based on it works. The universe really is this strange. And once you accept that, once you let go of the expectation that reality should make intuitive sense, a whole new world opens up. You start to see the universe not as a collection of solid, definite things, but as a shimmering web of possibilities, of superpositions and entanglements, of quantum fields permeating all of space, giving rise to particles and forces and everything we see. You start to appreciate the deep interconnectedness of everything, the way that measurement and observation play a role in shaping reality, the way that the quantum and classical worlds are not separate but intertwined. You start to grapple with the fundamental limits of knowledge, the inherent uncertainty built into the fabric of reality. And you start to wonder about the even deeper questions, the ones we haven't yet answered, the ones we might not even know how to ask. So what is quantum mechanics? It's a theory, yes, a mathematical framework for calculating probabilities and making predictions. But it's also more than that. It's a challenge to our understanding of reality. It's an invitation to think differently, to embrace strangeness, to accept mystery. It's a reminder that the universe is far more wonderful, far more intricate, far more profound than we ever imagined. And it's a foundation, a starting point for even deeper explorations, for theories we haven't yet conceived, for questions we haven't yet thought to ask. And I think that's what keeps physicists going, what drives them to spend years studying this strange theory, working through the math, designing experiments, debating interpretations. It's not just about solving problems or building technologies, though those are important. It's about understanding, it's about answering the fundamental question: what is the universe and how does it work? Quantum mechanics has given us part of the answer, a deep and surprising part. But it's not the whole answer. There's more to discover. And that sense of being on the edge of knowledge, of peering into the unknown, of making progress toward understanding the deepest nature of reality, that's what makes this so compelling, so endlessly fascinating. The quantum world is strange. It defies our expectations, challenges our assumptions, forces us to think in new ways. But it's also real, it's the foundation of everything, and we're lucky enough to live in a time when we can explore it, when we have the tools and the knowledge to probe its secrets, to test its predictions, to push the boundaries of what's known. That's a privilege and a responsibility, because understanding the universe, understanding how it works at its most fundamental level, that's one of the deepest, most meaningful things humans can do. It connects us to the cosmos, helps us see our place in it, gives us perspective on who we are and what existence means. So yes, quantum mechanics is weird, it's counterintuitive, it's hard to understand, but it's also beautiful, profound, and true. And grappling with it, trying to understand what it means, what it tells us about reality, that's one of the great intellectual adventures of our time. We're still in the middle of that adventure, still working out the implications, still asking questions. And I don't know where it will lead. Maybe we'll find a deeper theory that explains quantum mechanics, that shows why the universe is quantum. Maybe we'll develop a complete theory of quantum gravity, unifying all the forces and explaining the structure of space-time. Maybe we'll answer the measurement problem, understand what causes wave function collapse, figure out what's really going on in a quantum measurement. Or maybe we'll discover that reality is even stranger than we thought, that there are layers beneath quantum mechanics that we haven't yet imagined. I don't know, but I'm excited to find out. And I think you should be too. Because this is the story of how we came to understand the universe, and it's a story that's still being written. The quantum world is strange, yes. But it's our world, and learning to see it as it truly is, that's one of the greatest achievements of human knowledge. Now let's move on to another theory for you to reflect on. I've been thinking a lot about space lately, and specifically about this really strange, counterintuitive thing that happens with the universe. Something that when you first hear it sounds completely wrong, like it violates everything we know about physics. And maybe you've heard this before, maybe someone's mentioned it to you, but I wonder if you've really sat with it, really thought about what it means. Because here's the thing, here's this fact that scientists will tell you with complete confidence: space itself is expanding, and it's expanding faster than the speed of light. And when you hear that, your brain probably does what mine did the first time, which is to immediately protest, to say, wait, hold on, that can't be right. Because we all know, right? We all learned at some point that nothing can travel faster than light. It's the cosmic speed limit, the ultimate rule of the universe, the thing that Einstein showed us more than a century ago. Nothing, absolutely nothing, can break that barrier. And yet here we are, being told that space itself is doing exactly that, expanding at speeds that dwarf the speed of light, that make light look slow by comparison. So what's going on here? Is this a contradiction? Are physicists just making stuff up? Or is there something deeper, something stranger, something more beautiful happening that we need to understand? You see, the problem starts with how we think about speed, about motion, about what it means for something to move. We've got this intuitive understanding built from everyday experience, right? When something moves fast, it's because it's pushing through space, covering distance, going from point A to point B. A car driving down the highway, a plane flying through the air, even light itself beaming from a flashlight to the wall. All of these things are moving through space. They're traversing distance. They're going somewhere. And we can measure that. We can time it. We can calculate speeds and velocities. And all of that makes perfect sense. And the speed of light, well, that's just the fastest version of that kind of motion. Light moves through space at 299,792,458 meters per second, and nothing can move through space faster than that. That's the rule. That's what special relativity tells us. If you try to accelerate something, anything, to the speed of light, you'd need infinite energy. The faster you go, the more massive you become, the more energy you need to go even faster, and you can never, ever reach that ultimate speed. Light gets to travel at light speed because photons are massless, but anything with mass, forget about it. You're stuck below that limit forever. But here's where things start to get interesting, where the whole picture begins to shift. Because when we talk about space expanding faster than light, we're not talking about something moving through space. We're talking about space itself changing, growing, stretching. And that, well, that's a completely different beast. It's not motion in the traditional sense. It's not something traveling from here to there. It's the fabric of reality itself, the stage on which everything else happens, getting bigger. And the rules about the speed of light, those rules about cosmic speed limits, they apply to motion through space, not to the expansion of space itself. You see the difference? It's subtle, but it's crucial. It's the difference between a runner sprinting across a track and the track itself stretching while the runner stands still. The runner has a speed limit, sure, but the track can do whatever it wants. Let me back up a bit though, because I'm getting ahead of myself. Let's start with what we actually mean when we say space is expanding. Because space, right, we think of it as nothing, as emptiness, as the absence of stuff. It's just the gap between things. How can nothing expand? What does it even mean for empty space to grow? And I think this is where a lot of the confusion comes from, this idea that space is just nothing, just a void. But that's not quite right. Space, in the context of modern physics, in the framework of Einstein's general relativity, space is something. It's a thing, a real physical thing with properties and structure. It's not just the absence of matter, it's the fabric of the universe itself, the geometry that determines how things move, how light travels, how gravity works. When Einstein revolutionized physics in 1915 with general relativity, one of the key insights was that space and time aren't separate, fixed, unchanging backgrounds against which the universe unfolds. They're dynamic, they're flexible, they can bend, they can curve, they can stretch and compress. Massive objects like stars and planets don't just sit in space, they warp space around them. They create curves and dimples in the fabric of space-time, and those curves are what we experience as gravity. And if space can bend and curve, if it can be distorted by matter and energy, then why can't it also expand? Why can't the distances between points in space grow over time? Not because things are moving apart through space, but because space itself is getting bigger. That's the realization that changed everything, that opened up a completely new way of understanding the universe. And it all started really with observations, with what we could actually see when we looked out at the cosmos. In the 1920s, there was this astronomer, Edwin Hubble, working at the Mount Wilson Observatory in California, and he was studying distant galaxies, trying to measure their properties, their distances, their motions. And what he found was astonishing. He found that almost every galaxy he looked at was moving away from us. Not just a few, not just some random subset, but basically all of them in every direction, The light from these galaxies was shifted toward the red end of the spectrum, red shifted, which is what happens when a light source is moving away from you. It's the Doppler effect, the same thing that makes an ambulance siren sound lower pitched as it drives away. As the source moves away, the waves get stretched out, and for light, that means the wavelength gets longer, shifted toward the red. But here's what was really remarkable, what made this discovery so profound. Hubble noticed that the farther away a galaxy was, the faster it seemed to be moving away. It wasn't random. There was a pattern, a relationship. Galaxies twice as far away were moving away twice as fast. Galaxies 10 times as far away were receding 10 times as fast. And that told you something fundamental about the universe. If everything is moving away from us and the speed of recession is proportional to distance, then that means the universe itself is expanding. It's not that galaxies are flying through space away from us, like shrapnel from an explosion. It's that the space between us and them is growing, stretching, increasing over time. Every bit of space, everywhere in the universe, is expanding. And the more space there is between two objects, the faster they appear to recede from each other. Think about it like this, and this is an analogy that gets used a lot, but I think it's really helpful. Imagine the universe as the surface of a balloon, and galaxies are dots marked on that surface. Now, you're not inside the balloon or outside it. You're constrained to the surface. That two-dimensional surface is your entire universe. When you blow up the balloon, when you inflate it, what happens to the dots? They move apart, right? They get farther from each other. But none of them are actually moving across the surface of the balloon. Each dot is staying in its same spot on the rubber. What's changing is the rubber itself. The surface itself is stretching, expanding, and as it does, the distance between any two dots increases. And the farther apart two dots are to begin with, the faster they separate, because there's more rubber between them that's expanding. That's what's happening with the universe. Space is the balloon surface, galaxies are the dots, and the whole thing is expanding, growing, stretching in all directions at once. Now you might be wondering, if everything is moving away from us, doesn't that mean we're at the center? Doesn't that put us in some special position? And the answer is no, not at all. Every galaxy sees the same thing. If you were in any other galaxy, looking out at the universe, you'd see all the other galaxies moving away from you too, with the same relationship between distance and speed. There's no center to this expansion, no special point from which everything is fleeing. It's happening everywhere, uniformly, throughout space. It's a property of space itself, not a property of any particular location in space. And that's kind of beautiful, actually, this idea that the universe has no center, that every point is equivalent, that we're all seeing the same cosmic expansion from our own perspective. But let's get back to this speed thing, this faster than light business, because that's what we're really trying to understand here. Hubble's law, the relationship he discovered, can be written pretty simply. The velocity at which a galaxy appears to recede from us is equal to the Hubble constant multiplied by the distance to that galaxy. The Hubble constant, which we now know is about 70 kilometers per second per megaparsec, tells you how fast the expansion is happening. A megaparsec is about 3.26 million light years. So what this means is that for every 3.26 million light years of distance between us and a galaxy, that galaxy is receding at an additional 70 kilometers per second. So a galaxy that's 3.26 million light years away is receding at 70 kilometers per second. A galaxy that's 6.52 million light years away is receding at 140 kilometers per second. A galaxy 32.6 million light years away is receding at 700 kilometers per second. You see where this is going? The farther out you look, the faster the recession speed. And there's no limit to this, no point where it stops. If you go far enough, if you look at galaxies billions and billions of light years away, the recession velocity exceeds the speed of light. And that sounds wrong, right? That sounds like we've broken physics. But we haven't. And here's why. Those galaxies aren't moving through space faster than light. The space between us and them is expanding, and there's no limit on how fast space can expand. The speed of light is a limit on how fast information, matter, energy can move through space, but space itself isn't bound by that rule. Space isn't moving, it's expanding. It's a fundamentally different phenomenon. It's like the difference between swimming upstream in a river and the river itself widening. If you're swimming and the river is flowing faster than you can swim, you'll never make progress upstream. but that doesn't mean you're breaking any rules about how fast you can swim. The river's flow is independent of your swimming speed. In the same way, the expansion of space is independent of the speed of light. They're different things governed by different physics. Let me try to make this even clearer, because I think this is where people really struggle with the concept. Imagine you have two galaxies, A and B, separated by some vast distance. Let's say they're so far apart that the space between them is expanding such that they're receding from each other at twice the speed of light. Now, nothing in galaxy A is moving through space faster than light. Nothing in galaxy B is moving through space faster than light. If you were to measure the velocity of any object in either galaxy relative to the space immediately around it, you'd find speeds well below the speed of light. Everything is obeying the cosmic speed limit locally. But when you look at the rate at which the distance between A and B is changing, when you account for the expansion of all the space between them, you find that they're separating faster than light. The expansion has accumulated over all that distance, and it adds up to something superluminal. Here's another way to think about it. Imagine you're on a really, really long rubber band, and you're trying to walk from one end to the other. You can only walk at a certain speed, say 1 meter per second. That's your speed limit, your personal cosmic speed limit. But while you're walking, the rubber band is stretching, expanding. Every meter of rubber band is getting longer. If the rubber band is short, this doesn't matter much. You can still make progress, you can still reach the other end, even though it's getting farther away as you walk. But if the rubber band is long enough, if there are thousands and thousands of meters of rubber between you and your destination, the cumulative expansion can be faster than you can walk. For every meter you move forward, the rubber behind you and ahead of you is stretching, adding more distance. And if the rubber band is really long, the total rate at which the far end is receding from you can exceed your walking speed. You're not walking faster than your speed limit, you're not breaking any rules, but you can never reach the far end because it's receding faster than you can approach it. That's what's happening with distant galaxies. Light is the walker, the expansion of space is the stretching rubber band. And if there's enough space expanding between us and a distant galaxy, that galaxy is receding faster than light can travel toward it. Now, this raises some really interesting and somewhat disturbing questions. If there are galaxies receding from us faster than light, does that mean we can never see them? Does that mean we can never communicate with them? Does that mean there are parts of the universe that are forever beyond our reach, causally disconnected from us? And the answer, well, it's complicated, but essentially yes. There is a boundary, a cosmic horizon, beyond which we cannot see and never will be able to see. The light from galaxies beyond this horizon is trying to reach us. Those photons are traveling toward us at the speed of light, but the space between us and them is expanding so fast that the photons are losing ground. They're like runners on a treadmill that's going faster than they can run. They're moving toward us, but they're also being carried away by the expansion of space, and the net result is that they never get here. They never reach us. The distance between us and them keeps growing despite their best efforts to close the gap. And this cosmic horizon, this boundary between what we can see and what we can't, is not at the same place for everyone. It's relative to the observer. From our perspective here on Earth, there's a certain distance beyond which galaxies are receding too fast for their light to ever reach us. But from the perspective of a galaxy near that boundary, looking back at us, they have their own horizon, and we might be near their horizon. Every observer in the universe has their own observable universe, their own sphere of visibility, defined by the expansion of space and the speed of light. And the really unsettling thing is that as time goes on, as the universe continues to expand, this observable universe doesn't necessarily grow. In fact, in some ways, it's getting smaller. Galaxies that we can see now will eventually cross our cosmic horizon and disappear from view forever, as the expansion of space carries them away faster than their light can reach us. But let's back up even more, because I want to talk about how we even know that space is expanding in the first place, how we went from just seeing galaxies moving apart to understanding that it's space itself that's expanding. Because that's not an obvious leap. When Hubble first made his observations, you could have interpreted them differently. You could have said, okay, there was some kind of explosion in the past. All the galaxies were flung outward from some central point, and now they're just coasting through space, moving away from each other due to the momentum from that initial explosion. That would explain why distant galaxies are moving faster, because they got a bigger kick from the explosion. That would be the obvious, intuitive explanation, and it wouldn't require any weird ideas about space itself expanding. But that interpretation doesn't really work, and here's why. If galaxies were just moving through space, if this was ordinary motion, then we'd expect to see all sorts of patterns in their velocities. Some galaxies would be moving toward us, some away, some would be moving faster or slower than we'd predict based on distance alone. There'd be randomness, variation, or all the messiness of individual motions. But what we actually see is incredibly uniform. Almost every galaxy in every direction is redshifted, and the redshift is precisely proportional to distance. That level of uniformity, that exact relationship, suggests something more fundamental than just objects flying through space. It suggests that space itself has a property, a dynamic quality that governs these motions. And when you plug this idea into Einstein's equations of general relativity, when you ask what kind of universe could produce this pattern, you get a universe where space is expanding. You get a universe where the metric, the mathematical description of distances and geometry, is changing over time. The equations don't just allow for this possibility, they practically demand it given the observations. And there's another piece of evidence, something really profound that came out of understanding the expansion: the cosmic microwave background radiation. See, if space has been expanding, if galaxies have been moving apart over time, then in the past they must have been closer together, much closer. If you run the expansion backward, if you rewind the clock, you find that the universe was denser in the past, hotter in the past. And if you go back far enough, you reach a point where the entire universe was incredibly hot and dense, a state of extreme energy and temperature that we call the Big Bang. Now that's a misleading name, because it wasn't an explosion in space, it was the beginning of space itself, the beginning of the expansion. But anyway, if the universe started in this hot, dense state and has been expanding and cooling ever since, then there should be a remnant of that early heat, a faint afterglow of the Big Bang, still permeating all of space. And in 1964, two scientists, Arno Penzias and Robert Wilson, accidentally discovered exactly that. They were working with a radio antenna, trying to track down a mysterious noise, a hiss that seemed to come from everywhere at once. They thought it was interference, maybe from pigeons nesting in the antenna, but no matter what they did, they couldn't get rid of it. It turned out to be the cosmic microwave background, radiation from the early universe, stretched by the expansion of space from high-energy gamma rays to low-energy microwaves. This radiation is everywhere, coming from all directions, uniform to an astonishing degree, and it's exactly what you'd expect if the universe started from a hot, dense state and has been expanding ever since. The photons from that early era have been traveling through space for billions of years, and as space expanded, their wavelengths got stretched too, redshifted from visible light to infrared to microwaves. It's one of the most beautiful confirmations of the Big Bang model, this idea that we can still detect the heat from the birth of the universe, cooled now to just a few degrees above absolute zero. So we've got the expansion of space, we've got galaxies receding from us, we've got this cosmic microwave background, all of it consistent with a universe that started small and hot and has been expanding and cooling for about 13.8 billion years. But here's where things get really strange, where the faster than light expansion becomes not just a theoretical possibility, but a necessity. In the very, very early universe, in the first tiny fractions of a second after the Big Bang, physicists think there was a period of incredibly rapid expansion, far faster than the current expansion rate. This is called cosmic inflation, and it's one of the most important ideas in modern cosmology. The idea is that for a brief moment, maybe 10 to the minus 36 seconds after the Big Bang, the universe underwent exponential expansion, doubling in size over and over again in rapid succession, expanding by a factor of at least 10 to the 26th power in a time shorter than you can blink. And during this period, space was expanding far, far faster than the speed of light. Regions of space that were initially in contact, that could exchange information and energy, were suddenly separated by vast distances, carried apart by the inflation, moving away from each other faster than light could travel between them. Why would this happen? Well, the theoretical mechanism involves something called a scalar field. a kind of energy field that permeated space in the early universe. This field had a peculiar property. Instead of causing space to contract due to gravity, the way normal matter and energy do, it caused space to expand and to expand exponentially. The energy density of this field remained roughly constant even as space expanded, which meant that as more space came into existence, there was more energy to drive more expansion, which created more space, which had more energy, and so on in a runaway process. This is very different from normal matter, which gets diluted as space expands. If you have a certain amount of matter in a volume of space and that volume doubles, the density of matter is halved. But with this inflationary field, the density stayed the same, and that's what drove the exponential growth. And this solves several puzzles about the universe. For one, it explains why the universe is so uniform, why the cosmic microwave background has the same temperature in all directions to within 1 part in 100,000. If the universe hadn't undergone inflation, regions of space that we see on opposite sides of the sky would never have been in causal contact. They would never have been able to exchange information, so there'd be no reason for them to have the same temperature. But if they started out close together in contact during the pre-inflation era and then were rapidly separated by inflation, that would explain the uniformity. They were all part of the same hot, dense region initially, and then inflation stretched that tiny uniform region to encompass the entire observable universe. Inflation also explains the large-scale structure of the universe, the way galaxies are distributed. Quantum fluctuations in the inflationary field, tiny random variations in the energy density, got stretched to cosmic scales by the expansion, and these became the seeds for galaxy formation, the slight overdensities that attracted more matter and eventually collapsed into the galaxies and clusters we see today. So inflation is this remarkable, almost unbelievable idea that the universe underwent a period of faster-than-light expansion right at the beginning, and this explains so much about what we observe. And the thing is, there's nothing in the laws of physics that prevents this. General relativity allows for it. The expansion of space is not constrained by the speed of light. The speed of light limits motion through space, but space itself can expand as fast as it wants, and during inflation, it expanded at a phenomenal rate, far exceeding the speed of light. Regions of space were being separated so rapidly that light couldn't keep up, couldn't traverse the growing distances. And that's actually fine, that's perfectly consistent with relativity, because no information was being transmitted faster than light. No signal, no particle, no causal influence was moving through space faster than light. It was space itself that was expanding, carrying things along with it. Now, fast forward to today, to the universe we live in now. The inflationary epoch ended long ago within the first second of the universe's existence. After that, the expansion continued, but at a much slower rate, dominated by the matter and radiation in the universe. For billions of years, the expansion was decelerating, slowing down over time due to the gravitational attraction of all the matter pulling back on itself. But then, in the late 1990s, astronomers made an astonishing discovery, one that completely changed our understanding of the universe's fate. They were studying distant supernovae, using them as standard candles to measure cosmic distances and the expansion rate. And what they found was that the expansion isn't slowing down, it's speeding up. The universe is not just expanding, it's accelerating, expanding faster and faster as time goes on. This was a shock. It was completely unexpected. If the universe is full of matter, and matter has gravity and gravity is attractive, then the expansion should be slowing down, not speeding up. What could possibly cause acceleration? The answer, or at least the name we give to the answer, is dark energy. This is some kind of energy that permeates all of space, and unlike matter, it doesn't get diluted as space expands. Its density remains constant, or nearly so, even as the universe grows. And this dark energy has a repulsive gravitational effect. It pushes space apart, drives the acceleration. We don't know what dark energy is, we don't understand its nature, we just know that it exists because we can see its effects on the expansion. And it makes up about 68% of the total energy content of the universe, which is kind of staggering. Most of the universe is made of something we don't understand. And here's the thing, as the universe continues to expand and accelerate, driven by dark energy, more and more galaxies are going to cross that cosmic horizon I mentioned earlier. Right now we can see galaxies that are billions of light years away, some of them receding faster than light, but whose light was emitted in the past when they were closer and not yet receding that fast. But as time goes on, as the acceleration continues, the observable universe, the region from which light can reach us, is going to shrink. Galaxies that we can see now will become invisible. Their light will no longer be able to reach us. They'll cross the horizon and disappear from view forever. In the distant future, trillions of years from now, intelligent beings in our galaxy, if they exist, will look out at the universe and see only our local cluster of galaxies. Everything else will be beyond the horizon, invisible, unreachable. The universe will appear to be a much smaller, lonelier place. So let me try to bring all this together to really nail down what's happening here and why it's so counterintuitive. The speed of light is a fundamental constant of the universe, a speed limit that applies to anything moving through space. This comes from special relativity, from the structure of space-time itself, and it's inviolable. Nothing with mass can reach the speed of light, and no information can be transmitted faster than light. That's an absolute rule when we're talking about motion through space, about objects moving from one point to another in a fixed spatial framework. But space itself is not fixed. Space is dynamic, it's part of space-time, and according to general relativity, it can curve, it can bend, it can expand or contract. The expansion of space is not motion through space, it's a change in the metric, in the geometry of space-time itself. And there's no speed limit on how fast this can happen. When we say distant galaxies are receding faster than light, we're not saying anything in those galaxies is moving faster than light. We're saying the distance between us and them is increasing faster than light could traverse it. And that increase is due to the expansion of space. Every bit of space, every cubic meter, every infinitesimal volume element is expanding. And when you add up the expansion across billions of light years, the cumulative effect can exceed the speed of light. It's like compound interest. A small growth rate applied over a large amount accumulates to something significant. Each little bit of space is expanding at a rate that's perfectly fine, not violating any rules, but across vast distances, it adds up to something superluminal. And this has profound implications. It means there are parts of the universe we can never see, never reach, never communicate with. It means the observable universe has a boundary, and that boundary is set by the expansion of space. It means the universe is much, much larger than what we can observe, possibly infinite, but we're confined to seeing only our local patch, our cosmic neighborhood. Galaxies outside our observable universe are not just far away, they're beyond reach in a fundamental sense, separated from us not by distance alone, but by the structure of space-time itself. Their light will never reach us. Our light will never reach them because the space between us is expanding too fast. And here's something that really bends the mind. This means that in some sense, parts of the universe are moving away from us faster than the speed of light right now, at this very moment. Not in the past, not in some distant future, but now. There are galaxies out there whose current distance from us is increasing at superluminal speeds due to the expansion of space. We can't see their current state because the light showing us their current state hasn't reached us yet and never will. But right now, in the present moment, as defined by our reference frame, they're receding faster than light. And that's okay, that's perfectly consistent with physics because they're not moving through space faster than light. The space between us is expanding faster than light, and that's allowed. This also means that the universe doesn't have a center in the conventional sense. The Big Bang didn't happen at a point in space, it happened everywhere at once. Every point in space was part of the Big Bang, because space itself emerged from that initial state. When we talk about the universe being 13, 8 billion years old, we're talking about the time since the Big Bang, but the Big Bang itself wasn't an event located somewhere in space, it was the beginning of space. And as space has expanded, every point has remained at the center of its own observable universe. From our perspective, we see galaxies receding in all directions, with the most distant ones at the edge of our observable universe. But an observer in one of those distant galaxies would see the same thing from their perspective. They'd see galaxies receding in all directions, with us at the edge of their observable universe. There's no preferred location, no special center point. The expansion is homogeneous and isotropic, the same everywhere and in all directions, at least on large scales. Now, I want to talk a bit about what this means philosophically, existentially, because I think that's where the real weight of this idea hits you. We live in a universe that's expanding, and not just expanding, but accelerating in its expansion, driven by some mysterious dark energy we don't understand. Most of the universe is already beyond our reach, causally disconnected from us, and more of it is crossing that boundary every day. The universe we can interact with, the universe we can observe and study and potentially explore, is finite and shrinking. That's kind of a lonely thought. It means there are galaxies, stars, planets, possibly civilizations that we will never know about, never communicate with, never even detect, because the space between us is expanding too fast. They're out there somewhere, maybe asking the same questions we are, looking up at their night sky and wondering what else is out there. But we're separated by something more fundamental than distance. We're separated by the structure of space-time itself. And yet, there's something beautiful about it too, something profound. The fact that we can understand this, that we can use mathematics and observation and reason to figure out that space is expanding faster than light, that we can trace the history of the universe back to its beginning, that we can predict its future, that's extraordinary. We're these small, fragile beings living on a tiny rock orbiting an average star in an unremarkable galaxy, and yet we've figured out the fundamental nature of the cosmos. We've understood something that seems impossible on its face, this idea that space can expand faster than light without violating the laws of physics. We've reconciled the apparent contradiction. We've made sense of the universe's large-scale structure and evolution. That's an incredible achievement of human intellect and curiosity. But let's dig even deeper into the mechanics of this, because I want to make sure we really understand what's happening at a technical level, even if we're explaining it conceptually. In general relativity, the geometry of space-time is described by something called the metric, which is essentially a mathematical rule that tells you how to calculate distances and time intervals between events. In a flat, static space-time like the one we deal with in everyday life and in special relativity, the metric is simple and unchanging. Distances don't change over time, and the geometry is Euclidean. But in an expanding universe, the metric itself is changing. The rule for calculating distances is evolving as time passes. This is called a time-dependent metric, and it's what describes the expansion of space. The specific metric that describes our universe on large scales is called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric for short, named after the scientists who developed it. This metric describes a homogeneous and isotropic universe, one that looks the same everywhere and in all directions on large scales, which is a pretty good approximation for our actual universe. In this metric, there's a function called the scale factor, usually denoted by the letter A, which tells you how much space has expanded at any given time. As time increases, the scale factor increases, and distances between any 2 points in space scale with this factor. If the scale factor doubles, all distances double. If it triples, all distances triple. The rate at which the scale factor changes is what determines the expansion rate of the universe. And here's the key. The rate of change of the scale factor divided by the scale factor itself gives you the Hubble parameter, which tells you how fast space is expanding at any given moment. Right now, the Hubble parameter has a value of about 70 kilometers per second per megaparsec, as I mentioned earlier. This means that for every megaparsec of distance, space is expanding such that objects appear to recede at 70 kilometers per second. But the Hubble parameter itself changes over time. In the early universe, it was much larger, meaning the expansion was faster. As the universe expanded and matter became more dilute, the expansion slowed down and the Hubble parameter decreased. But then, when dark energy started to dominate, the expansion began to accelerate again. And while the Hubble parameter isn't increasing now, the expansion rate is, which means the rate of change of the scale factor is increasing. Now, when we calculate the recession velocity of a distant galaxy using this framework, we multiply the Hubble parameter by the distance to the galaxy. This gives us what's called the recession velocity, and it can exceed the speed of light for sufficiently distant galaxies. But this recession velocity is not a velocity through space, in the usual sense. It's not the velocity you'd measure locally if you were sitting next to the galaxy with a speedometer. It's a coordinate velocity, a velocity that arises from the change in the metric, from the expansion of space. And in general relativity, coordinate velocities can exceed the speed of light. That's fine. What can't exceed the speed of light is the local velocity, the velocity of an object moving through the space-time immediately around it. That's always less than c, the speed of light, for any massive object. So there's this distinction between proper motion, which is motion through space and is limited to subluminal speeds, and the apparent motion due to the expansion of space, which is not limited. A galaxy can have zero proper motion relative to the expanding universe, meaning it's just going with the flow, not moving through space at all, and yet it can still be receding from us faster than light due to the expansion. In fact, that's the situation for most distant galaxies. They're not flying through space away from us. They're stationary, or nearly so, relative to the expanding cosmic framework, and it's the expansion itself that's creating the separation. This also helps explain something that might seem paradoxical. If galaxies are receding faster than light, how did their light ever reach us? Shouldn't the light be stuck, unable to make progress toward us because it's being carried away by the expansion faster than it can travel? And the answer is that the expansion rate changes with time and is different at different distances. When the light from a distant galaxy was emitted, the galaxy might have been receding faster than light even then, and the photons initially moved away from us in terms of coordinate distance. They were emitted in our direction, but the expansion of space between us and them was carrying them away faster than they were approaching us. But as time went on, as the universe expanded and the light entered regions of space where the expansion rate was lower, the photons started making progress. They entered our Hubble sphere, the region where the recession velocity is less than the speed of light, and once inside, they could make their way to us. It's like swimming upstream in a river that gradually becomes slower as you go. At first, you're losing ground, being carried downstream even as you swim upriver, but eventually, you reach a section where the current is slower than your swimming speed, and you can make progress. The Hubble sphere is this boundary where the recession velocity equals the speed of light. Galaxies inside the Hubble sphere are receding slower than light and can, in principle, send light to us that will eventually arrive. Galaxies outside the Hubble sphere are receding faster than light, and light they emit now will never reach us. But light they emitted in the past, when they were closer and inside the Hubble sphere, can still reach us. That's why we can see galaxies that are currently receding faster than light. We're seeing them as they were in the past, and the light we're receiving was emitted when conditions were different. And this brings up the concept of the particle horizon, which is different from the Hubble sphere. The particle horizon is the boundary of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang. It's set by the age of the universe and the speed of light, but it's not simply the age of the universe times the speed of light, because the universe has been expanding all that time, stretching the distances. The actual particle horizon is at a co-moving distance of about 46 billion light years, even though the universe is only 13.8 billion years old. This is because the space between us and the most distant observable objects has been expanding while the light was traveling to us, so the objects are now farther away than their light travel time would suggest. Beyond the particle horizon, there are regions of space from which light hasn't had time to reach us yet, not because the light is traveling too slowly, but because those regions were too far away at the time of the Big Bang for their light to have gotten here in the time available. And if the expansion continues to accelerate, there will also be an event horizon, a boundary beyond which events happening now will never be observable by us, no matter how long we wait. Light emitted from beyond the event horizon today will never reach us, because the expansion will carry it away faster than it can approach. The event horizon is at a co-moving distance of about 16 billion light-years currently, and it's not growing as fast as the particle horizon, which means the two are converging. Eventually, in the far future, the observable universe will approach a limit defined by the event horizon and will never see anything beyond that. This is the long-term fate of the universe, given our current understanding. If dark energy continues to dominate and the acceleration continues, the universe will undergo what's sometimes called the Big Rip, or heat death, depending on the exact properties of dark energy. In the Big Rip scenario, if dark energy's density actually increases over time rather than remaining constant, the expansion accelerates more and more until eventually the forces holding atoms together, even the forces holding nuclei together, are overcome by the expansion. Space itself is torn apart at the smallest scales, and the universe ends in a cataclysmic disintegration. But most physicists think dark energy is more likely to be a cosmological constant with a fixed density, in which case the universe just continues expanding and accelerating forever, becoming colder, emptier, darker as stars burn out and galaxies drift apart, eventually reaching a state of maximum entropy and minimum energy density, a heat death where nothing interesting can happen anymore. But let's pull back from these apocalyptic scenarios and return to the central marvel here, the thing we're really trying to wrap our heads around. Space is expanding faster than light. Not space as in outer space, not the emptiness between planets or stars, but space as in the fundamental fabric of reality, the arena in which everything exists and moves. This fabric is stretching, growing, increasing in extent, and it's doing so at a rate that exceeds the universe's ultimate speed limit. And that's okay, that's allowed, that's consistent with everything we know about physics, because the speed limit applies to motion through space, not to the expansion of space itself. It's a distinction that's easy to miss, easy to gloss over, but it's absolutely crucial. Without understanding this distinction, the whole thing seems like a contradiction, a violation of relativity. With the distinction, it makes sense. It's counterintuitive, sure, but it's not inconsistent. It's just the way the universe works. And the evidence for this is overwhelming at this point. We have the redshift of galaxies, the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements from Big Bang nucleosynthesis, the observations of distant supernovae showing acceleration, all of it pointing to the same picture. A universe that started from a hot, dense state, expanded and cooled, and continues to expand and accelerate today. The Big Bang model, with its expanding space and faster-than-light recession velocities, is not speculative. It's the best supported scientific theory we have for the origin and evolution of the cosmos. It's been tested in countless ways, and it keeps passing the tests. That doesn't mean we understand everything. There are huge mysteries. What caused the Big Bang? What drove inflation? What is dark energy? What is dark matter? Are there other universes? What happened before the Big Bang, if there even was a before? These are open questions, frontiers of research. But the basic framework, the expanding universe with superluminal recession velocities, that's solid. That's established science. So what does it feel like, emotionally, existentially, to live in such a universe? I think there's something both humbling and exhilarating about it. Humbling because it reminds us how small we are, how limited our cosmic neighborhood is compared to the vastness of the universe beyond. Most of reality is forever beyond our reach, separated from us not by mere distance, but by the expansion of space-time itself. We'll never see most of the universe, never know what's out there, never contact civilizations that might exist in those unreachable regions. That's a kind of cosmic loneliness, a reminder of our isolation in the grand scheme of things. But it's also exhilarating because we've figured this out. Against all odds, we've understood something profoundly counterintuitive about the nature of reality. We've reconciled the apparent contradiction between the cosmic speed limit and the faster-than-light expansion. We've traced the history of the universe from its fiery beginning to the present day. We've made predictions about its future. That's the power of human reason and curiosity, the ability to go beyond immediate experience and intuition, to grasp truths that are hidden, subtle, strange. And there's beauty in the strangeness, isn't there? The universe doesn't have to make intuitive sense to us. It doesn't owe us comfort or simplicity. It just is what it is, and what it is turns out to be far more intricate and marvelous than we might have imagined. Space expanding faster than light, driven by mysterious dark energy, shaped by quantum fluctuations in the first moments after the Big Bang, curved by the presence of matter and energy, all of it described by elegant mathematical equations that connect geometry and physics in profound ways. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. I think he was getting at this idea that the universe could have been totally chaotic, random, impossible to understand, but instead it follows laws, patterns, rules that we can discover and describe. And those rules, when we understand them deeply enough, reveal a cosmos that's far stranger and more wonderful than common sense would suggest. Let me try to address one more aspect of this that I think is worth exploring, and that's the question of what this means for the ultimate nature of space and time. If space can expand, if it can change its geometry, if it's not some fixed eternal background but a dynamic, evolving entity, then what is it really? Is it a thing in itself, or is it just a relationship between objects? This is a deep question that philosophers and physicists have been arguing about for centuries, and the expansion of space adds a new dimension to the debate. In Newton's time, space was thought of as absolute, as a fixed framework that existed independently of the objects in it. You could imagine removing all the matter and energy from the universe, and space would still be there, an infinite, unchanging void. But Einstein's relativity challenged this view. In relativity, space and time are not absolute. They're relative, they depend on the observer, and they're intimately connected to matter and energy. The presence of mass and energy curves space-time, and the curvature of space-time tells objects how to move. Space, in this view, is more like a field, a dynamic entity that interacts with everything else. And the expansion makes this even clearer. If space were just nothing, just the absence of things, then expansion wouldn't mean anything. How can nothing expand? But if space is a field, a physical thing with properties, then expansion makes sense. The field is growing, its extent is increasing. And this raises fascinating questions about the nature of the field. What gives space its properties? Why does it expand? What is dark energy, the force or field or whatever it is that drives the accelerating expansion? We don't have complete answers to these questions. Dark energy might be the energy of empty space itself, what's called vacuum energy, or the cosmological constant. Quantum field theory suggests that even empty space, even a perfect vacuum, isn't truly empty, but is seething with virtual particles popping in and out of existence. And this quantum activity might have an energy associated with it. But when physicists calculate what the vacuum energy should be based on quantum mechanics, they get a value that's vastly larger than what we observe for dark energy, off by a factor of 10 to the power of 120 or so. That's probably the worst prediction in the history of science. And it suggests we're missing something fundamental about how quantum mechanics and gravity fit together. Some physicists think dark energy might not be a constant, but a field that varies over time and space, something called quintessence. Others think it might be a sign that general relativity needs to be modified on cosmological scales. There are even speculations that the accelerating expansion is evidence of extra dimensions or a multiverse, though these ideas are highly speculative and not well supported by current evidence. The point is, we don't really know what dark energy is, which means we don't fully understand why space is expanding, let alone why it's accelerating. We can describe what's happening, we can measure it, we can predict its effects, but the underlying cause remains mysterious. And that's okay, that's how science works. We build models that explain the observations, and when the models work, we use them, even if we don't understand every detail. And we keep investigating, keep testing, keep trying to dig deeper into the underlying mechanisms. There's also the question of whether space is infinite or finite. The expansion doesn't really answer this. An infinite space can expand just as easily as a finite one. If space is infinite, it was always infinite, even at the Big Bang. The Big Bang didn't create space from nothing. It was a state where all of space, infinite or not, was extremely hot and dense. As space expanded, the density decreased, but if space was infinite, it remained infinite. On the other hand, if space is finite, if the universe has a finite volume that wraps around on itself in some way, like the surface of a sphere wrapping around in 2 dimensions but extended to 3 dimensions, then the expansion means this volume is growing over time. Current observations suggest that if space is finite, it's large enough that we can't see the wraparound. The universe appears flat, not curved, on the largest scales we can observe, which means that if it's finite, it's much, much larger than the observable universe. So we might never know for sure whether space is infinite or just really, really big. And then there's the beginning, the Big Bang itself. If space has been expanding and we run that expansion backward in time, we get to a point about 13.8 billion years ago where all the space we can see was compressed to a tiny volume, essentially a point. Density, temperature, and curvature all go to infinity in the equations, which is a sign that the equations are breaking down, that we're reaching the limits of general relativity's applicability. This singularity, as it's called, is where our current physics fails. We can't describe what happened at the exact moment of the Big Bang or what came before, if anything did come before. To go further, we'd need a theory of quantum gravity, a way to combine general relativity with quantum mechanics, and we don't have that yet. There are candidates like string theory and loop quantum gravity, but they're not yet complete or tested. So the very beginning of the universe, the origin of space and time themselves, remains one of the deepest mysteries in physics. Some people wonder whether the Big Bang was really the beginning or whether it was more like a transition, a bounce from a previous contracting phase. Maybe the universe is cyclic, expanding and contracting over and over, with each Big Bang being a big bounce from a previous state. Or maybe our universe is just one bubble in a vast multiverse, with other universes existing alongside ours, each with their own properties, their own laws of physics. These ideas are speculative, not well supported by evidence, but they're fun to think about, and they remind us that we still have so much to learn. The expansion of space, the faster-than-light recession of distant galaxies, these are pieces of the puzzle, but the puzzle itself is far from complete. What I find most striking, most moving about all of this is the sheer ambition of the scientific enterprise. Here we are, these small beings on a small planet, and we're trying to understand the entire universe, its origin, its evolution, its fate. We're using mathematics and observation and reason to figure out truths that are completely beyond everyday experience, truths that are counterintuitive and strange but nonetheless real. And we're making progress. We're actually figuring it out. Not completely, not perfectly, but substantially. We've gone from thinking the Earth was the center of everything to understanding that we're on a planet orbiting a star in a galaxy that's one of hundreds of billions in an expanding universe that started 13.8 billion years ago and is accelerating in its expansion due to dark energy. That's an incredible journey of discovery, and it's not over. There are still mysteries to solve, questions to answer, phenomena to explain, and the faster-than-light expansion of space is right at the heart of this. It's a phenomenon that challenges our intuitions, that forces us to think carefully about the difference between motion through space and the expansion of space itself. It's a reminder that the universe is under no obligation to conform to what we find comfortable or easy to understand. It just is what it is. And if we want to understand it, we have to meet it on its own terms. We have to let go of our preconceptions and follow the evidence wherever it leads. And where it leads, in this case, is to a cosmos that's far more dynamic, far more strange, far more magnificent than we might have guessed. Space itself is expanding, carrying galaxies with it, and in the most distant reaches, that expansion exceeds the speed of light, creating cosmic horizons beyond which we cannot see, separating us from vast regions of reality that we'll never be able to observe or interact with. But we know they're there. We know the universe extends far beyond what we can see, that there are galaxies and stars and planets, and maybe even life in places that are forever beyond our reach. And that knowledge, that understanding, is a testament to what the human mind can achieve when it turns its attention to the cosmos and asks, with humility and curiosity, what is this place, this universe we find ourselves in? How does it work? Where did it come from? Where is it going? These are some of the oldest questions, the deepest questions, and we've made progress on them, real progress. We don't have all the answers, we probably never will, but we've learned so much. And what we've learned is that the universe is even more wondrous than we imagined, a place where space can expand faster than light without breaking any rules, where the fabric of reality itself is dynamic and evolving, where mysteries abound but understanding is possible. So when you look up at the night sky, when you see the stars and know that between us and them, space is expanding, carrying them away, and beyond the visible stars, beyond the reach of our most powerful telescopes, there are galaxies receding faster than light, forever beyond our cosmic horizon. I hope you feel what I feel, a sense of awe, of wonder, of deep gratitude that we live in a time when we can understand these things, when we can peer into the nature of reality and glimpse truths that are both humbling and inspiring. The universe is vast, it's mostly beyond our reach, but it's also comprehensible, at least in part, and that makes all the difference. We're not just passive observers, we're participants in the grand project of understanding, and every answer we find, every mystery we solve, is a triumph of the human spirit, a demonstration of what's possible when curiosity meets rigor and imagination meets evidence. That's the real story here, not just the faster than light expansion of space, but our ability to discover it, to understand it, to make sense of something that seemed impossible, and find that it's actually a natural consequence of the laws that govern our universe. And that, I think, is worth celebrating.